To officially set the tone for today's event, I would like to invite you all to join me in a warm round of applause to celebrate this exciting beginning. Please. Thank you so much. And for those who may be joining us for the first time, allow me to briefly introduce about the InnovaConnect series. Initiated by the VinFuture Foundation in 2024, the InnovaConnect series served as a vital platform to foster direct academic exchange, connecting scientists, researchers, and experts to share knowledge and cultivate meaningful collaborations. Building on the successful pilot in Hanoi in 2024, the VinFuture Foundation has announced an expansion of an InnovaConnect series earlier this year. And we are especially pleased to commend this year's series here in Da Nang, one of the top-ranked cities in the 2024 Provincial Innovations Index announced by the Ministry of Science and Technology. It is a privilege to mark this expansion with our inaugural 2025 InnovaConnect event, jointly organized with our distinguished co-host, the University of Da Nang, University of Science and Education. Established in 1975, the University of Da Nang University of Science and Education is one of the 7 key teacher training universities in Vietnam. The university is dedicated to training and developing high-quality human resources, with teacher training at its core and conducting scientific research and technology transfer, aiming to contribute to national development, particularly in the central regions and highlands. The university offers programs from undergraduate to doctoral levels across natural science and technology, social science and humanities, and educational science. Their commitment to academic excellence and national development has made them an invaluable partner with us for this time. Now, let us delve deeper into the focus of today's event, innovative solutions and material for sustainable development. As the world grapples with escalating environmental challenge, finding sustainable alternative has never been more urgent. In this context, hydrogen emerged as a highly promising clean energy alternative, with water splittings recognized as one of the most environmentally sustainable production methods. Therefore, today's event brings together leading experts to exchange insights and foster collaborations for sustainable development in Vietnam and beyond. And now, it's my pleasure to introduce the esteemed panel joining us today. Representing our co-host, please welcome Associate Professor Dr. Văn Hiếu Nguyễn, Vice Rector of the University of Da Nang, University of Science and Education. Next is Associate Professor Dr. Minh Lý Nguyễn, Head of Department of Science, Information Technology, and International Cooperation. Dr. Văn Tắc Ninh, Vice Dean at Faculty of Physics and Chemistry. From the VinFuture Foundation, we're delighted to have Dr. Thái Hà Lê, Managing Director. Mr. Cảnh Toàn Quách, Director of Marketing and CSR Programs. Finally, Mr. Gia Khánh Nguyễn, Acting Head of Operations. Joining them are 3 distinguished speakers who bring global perspective and deep expertise to today's event. Professor Yon Tae-ju from the Division of Advanced Material Engineering at Yeonbuk National University in South Korea. Dr. Hoàng Long Du from the School of Chemistry at Monash University in Australia. And finally, Associate Professor Dr. Võ Thắng Nguyên from the Faculty of Physics and Chemistry at the University of Da Nang, University of Science and Education. To hear the opening remarks from our distinguished co-hosts, please join me in welcoming Associate Professor Dr. Văn Hiếu Nguyễn, Vice Rector of the University, to the stage.
Ladies and gentlemen, distinguished guests, scholars, friends, good morning. It's a great honor for me, on behalf of University of Science and Education, University of Da Nang, to warmly welcome all of you to VinFuture InnovaConnect 2025, the first event kind have under inspiring theme, innovative solution, and material for sustainable development. Today, we are not just here to exchange knowledge. We are here to share commitment to solve some of the world's most urgent problems. Clean energy, sustainable material, and green technology. They are not challenging for your future. They are challenging we must face right now. We are proud to welcome standing speaker from Jeonbuk National University in South Korea, Monash University in Australia, and our University of Science and Education of Vietnam. The pioneering work reflects the spirit of innovation that this event all about. The topics that we share are not only current as in science, but also highly relevant to our future in energy, environment, and our global society. The world needs both idea and both action more than ever. Through programs like InnovaConnect, VinFuture has built bridge between research, real-world solutions, and international cooperation. VinFuture is not just recognizing great science, it's creating a culture where science serves humanity, a culture where innovation is practical, meaningful, and leads us to a better, more sustainable world. At our university, we proudly support this mission. We are building an academic environment that encourages global connection and empower our students and faculty to contribute to movement like VinFuture. Even like today, are vital in nurturing the next generation of scientists, engineers, and change makers, not just for Vietnam, but for the world. Let me end by wishing you productive and inspiring day learning, sharing, and connecting. May InnovaConnect 2025 spark not only new ideas, but also lasting partnership for more sustainable and fair future. Thank you so much.
Thank you, Associate Professor Dr. Van Hieu Nguyen, for your warm and inspiring remarks. And now, following those insightful words, I would like to invite Dr. Thái Hà Lê, Managing Director of the VinFuture Foundation, to deliver the welcome speech on behalf of the foundation. Please join me in welcoming Dr. Thái Hà Lê to the stage.
Very good day to everyone. Good morning and welcome to the InnovaConnect 2025. It is my great pleasure on behalf of the VinFuture Foundation to welcome you all, whether you are here with us in Da Nang or participating online via Zoom from across different regions. First and foremost, we would like to extend our sincere appreciation to our co-organizer, University of Science and Education, University of Da Nang, for their warm hospitality. It is a true pleasure to collaborate with an institution so committed to scientific excellence and sustainability. We are so truly delighted to be hosting this event in Da Nang, one of the most livable cities in Vietnam, where traditions meet modernity, where the mountains meet the seas, and where the seafood is as fresh as the idea we are going to hear today. And perhaps that's what makes Da Nang the perfect place to talk about sustainable development, because here the nature keeps reminding us daily about what we are working to protect for. And today's theme, innovative solutions and materials for sustainable development, is not just timely, it's also essential and deeply aligned with the mission of the VinFuture Foundation. We aim to promote breakthrough science and technology that serve humanity, especially in the global south. And in today's world, I believe that finding cleaner, smarter, and sustainable ways to power our future is one of the most urgent topics whatsoever, right? And we are also honored today to be joined by three outstanding speakers. Professor Yan Tae-yu, who will take us into the fascinating world of solar water splitting using advanced photocatalysts. Dr. Hoàng Long Du, who is exploring electrified ammonia synthesis, a key to unlocking a hydrogen future. And Associate Professor Dr. Võ Thắng Nguyên, who will share new approaches using MOF-based materials for catalytic applications. These are not just about technical presentations. They are examples of how science can rise to meet the new environmental challenges of our time. Research that seeks to improve life, protect our planet, and shape a more sustainable future for all. And at the VinFuture Foundation, we believe strongly in the power of collaboration between countries, between disciplines, and also between generations. InnovaConnect is part of that effort, a space where early-stage ideas can grow into real impact and where meaningful connections can spark new journeys. So whether you are here for the science, for the inspirations, or just for the curiosity, we thank you for being part of this journey. We look forward to a morning of meaningful discussion and perspective. Thank you very much, and let's begin.
Thank you, Dr. Tai Hale, for those insightful opening words. And now, to set the stage for our conversations, I would like to invite you all to watch a brief trailer that provides an overview of what we'll be discussing today. Please.
Environmental pollution driven by rapid industrial development, particularly water and air pollution, has become an urgent global issue. At the same time, depletion of fossil fuels due to unsustainable consumption has led to serious environmental consequences, forcing the world to make the imperative shift toward renewable energy sources. In that context, hydrogen is considered a highly promising clean energy source, with water splitting regarded as the most environmentally friendly method. To further explore solutions for sustainable development, the VinFuture Foundation is collaborating with the University of Da Nang, University of Science and Education, to host the inaugural InnovaConnect Event of 2025, themed Innovative Solutions and Materials for Sustainable Development. The seminar featured the esteemed panel of 3 distinguished speakers. Professor Yeon-Tai Yu, professor in the Division of Advanced Materials Engineering at Jeonbuk National University, South Korea, has extensive expertise in hydrothermal processing, functional fine particle synthesis, and crystal growth. His research centers on the synthesis and application of metallic nanoparticles and core shell nanostructures, particularly for use in photocatalysis, gas sensors, solar cells, fuel cells, and hydrogen production. The second distinguished speaker is Dr. Hong Long Yu, who has had nearly a decade of expertise in green ammonia synthesis for agricultural and energy applications. His most significant achievement is the breakthrough demonstration of lithium-mediated nitrogen reduction at nearly 100% current-to-ammonia efficiency, published in Nature. His research has led to the founding of Jupiter Ionics, an Australian green ammonia company, where he currently serves as an academic consultant. Last but not least is Associate Professor Dr. Vo Thang Nguyen from the University of Da Nang, University of Science and Education. Her research focuses on the development of novel materials for electrochemical and photocatalytic applications. She has been actively involved in several international research collaborations, including the EU-funded MoMA project, joint work with Jeonbuk National University, and a visiting lectureship at Mi University. With the participation from the esteemed panel, the event aims to promote scientific collaboration between domestic and international researchers to address and propose solutions to pressing environmental challenges in Vietnam and globally. Join us for the inaugural 2025 InnovaConnect Event, Innovative Solutions and Materials for Sustainable Development.
And now, it's my pleasure to introduce our first distinguished speakers, Professor Yeon-Tai Yu. Professor Yu is a leading expert in material science for sustainable development from the divisions of Advanced Material Engineering at Jeonbuk National University in South Korea. And today, he will be sharing the latest research updates on metal MOS core shell nanoparticle photocatalysts for sustainable solid water splitting. Please join me in welcoming Professor Yu to the stage.
Thank you. Very nice introduction of me. Okay. Yes. I would like to appreciate Dr. Miu, the Vice Director of this university, and other members of this university and members of VinFuture Foundation for organizing these meetings. And I'm very honored to be here to give this talk. Okay. I will start my speaking. Today's my talk title is Metal at MOS. MOS means metal oxide semiconductor. Co-shell nanoparticle photocatalysis for sustainable solar water splitting. This is my university sceneries at the daytime and sunset time. Very beautiful. Welcome to my university. Okay, this is the outline is for today's presentations. In the first part, I will mainly say the advanced co-shell nanoparticle integrated heterojunction photocatalyst. In the part 2, I will introduce briefly co-shell nanoparticle. In the third part, I will introduce our the recent research result on hydrogen evolution of the photocatalyst. Finally, I will mention conclusion and future work. As you know, the solar energy, a lot of solar energy is combined with the current, the electricity grid system. That's why the surplus electricity can be produced. The many the persons is interested in the production of hydrogen by using this surplus electricity. The interesting is the growing and growing. This green hydrogen, the market is also the growing and growing every year. The annual growth rate is the 40%, and then the global green hydrogen market in 2030 will be 61.35 billion US dollars. Green hydrogen by pure just electricity is too expensive. That's why we have to use some catalysts. There are 3 kinds of the catalyst. The first one is electro catalyst. Shows very high efficiency, but the cost is still high. The second photocatalyst, this photocatalyst is very cheap, but the efficiency is very low. We need to focus on today is photoelectrochemical catalyst. In this method, the electricity and light is used together. That's why the cost is quietly cheap, and the photohydrogen conversion efficiency is quietly high. But this the photocatalyst also have some problems we have to solve. The problem is the lack of solar light absorption, a lack of bifunctional ability for HER and OER the reactions, and pH dependence, low solar to hydrogen conversion efficiency, and also low stability. There are one of good methods to solve this kind of the problem. I think it is the heterojunctions of photocatalyst with other metals. There are the 4 different heterojunctions of catalyst. The first one, Schottky junction heterojunction. This junction is the combination of metal and metal oxide. And the first one, second one, G-scheme structure photocatalyst. Actually is the combination of metal oxide and metal oxide. Only the band gap is different, and the Fermi level position is different. Recently, this G-scheme structure photocatalysts have shown the very good performance. So let's see this the G-scheme structure photocatalyst structure. The electrons is let's see the electron movement. electron movement is the the looks like the G and the letter. So we say this heterojunction is called the G-scheme structure photocatalyst. Yeah, there are this G-scheme the photocatalyst is divided to the three different type according to their own the generation. First generation, the liquid phase mediate is used for the connecting these two material, metal oxide. One side is the OEP, one side is the HEP. OEP means the oxygen evolution photocatalyst. HEP means the hydrogen evolution photocatalyst. In second generations, instead of the liquid phase mediate, metal is used between the two the metal oxide, OEP and HEP. In third generation, these two, the metal oxide, OEP, HEP, is indirectly connect each other. So this, third generation photocatalyst, G-scheme photocatalyst shows the high performance. So we applied our material, the metal MOS porcelain particle to this G-scheme, third generation G-scheme photocatalyst. Figure D, below figures, that shows the porcelain particle integrated G-scheme structure photocatalyst. We call this material the advanced third generation photocatalyst. Yes, so in our lab, three different kind of porcelain particles applied to the G-scheme, applied. These are three materials. The first one is the ceria at gold ceria porcelain particle. Second one, silver tungstate at gold. The third one is the gold at zinc oxide porcelain particle. This three material is applied to the these Schottky-like junctions, second generation G-scheme heterojunctions, and advanced third generation G-scheme photocatalysts, respectively. I will today introduce this research week in the part 3. In this, the second part, I will introduce briefly what is the porcelain particle and their advantage. There are many kinds of porcelain particles, the metal to metals, oxide to metal to oxide, oxide to oxide, compounds, and to sulfide. Among these porcelain particles, I'm very interested in this, the metal to oxide porcelain particles, because this inner metal core can be protected by outer cell material, and the metal cores can be used as a good catalyst. So this porcelain particle can be used water splitting, gas sensing materials, fuel cell catalyst, and QD phosphor materials. In our lab, during over 20 years, we synthesized many kinds of porcelain particles. This page shows the metal at N-type semiconductor MOS porcelain particle. 6 different porcelain particles. And this page shows the metal at P, the MOS porcelain particle, and P MOS at NMOS porcelain particle, and metal at metal porcelain particles. Okay, let's move to the part 3. I will discuss in this part 3 about our the recent research results on hydrogen evolution photocatalyst by using these 3 different kinds of porcelain particles. The first photocatalyst is gold at ceria porcelain particles. The research results is already published in the Applied Catalyst B in 2021. So you can find this detail, the research result in this manuscript. As you can see in this TM image, you can confirm that gold ceria porcelain particle was perfectly synthesized. The figure D is the perfect porcelain particles. In this study, cerea's shell thickness was changed like that. The thickness is the 18 and 28 nanometer. And then this in this study, this photocatalytic activity was compared to shear ceria. This page shows the photocatalytic activity test result. As you can see in the upper middle, the figure. Gold at ceria nanoparticle with 18 the shell thickness, it showed the best performance. The hydrogen reduction rate is the 4.1 millimole per hour gram. This value is the 10 times higher than the pure ceria. Okay. Next is the mechanism for this the materials. This material looks like the Schottky heterojunction, but it's not exact Schottky junction, the heterojunctions, because the electron hole pair created from the inside gold core under the absorption of UV light. This electrons go to the state of ceria 3+. And then the electrons is the corrected the electron at the state of the ceria 3+, drive very strong hydrogen reduction reactions. Second, photocatalyst, the silver tungstate at silver and GIS nanocomposite, a little bit complicated the material, nanocomposite. In this study, we prepared the first two the nanoload. First one is the age-loaded silver tungstate. The second one is the silver the silver shelled. This silver shell is compactly covered with on the surface of silver the tungstate. Okay, if you and then we combined these ones combined with GIS the nanosheet. GIS meaning is the zinc indium sulfide material. You can find the perfect silver nanoshell layer on the deposited surface of the silver tungstate nanoloads in the figure of F. Okay, let's see the photocatalytic activity test result. In this study, we compared several materials. This silver tungstate and GIS, zinc indium sulfide, and other composites, other two composites. One is the silver loaded one is the silver shelled one. Yes. So yes, this the right side the result we can find this silver shelled silver tungstate zinc GIS nanocomposite shows highest the photocatalytic activity. This photocatalytic activity is quite relatively higher than compared to the previously developed photocatalyst. Yes. Okay, it is the mechanism. This mechanism is based on the explained based on the second generation heterojunction structure, because the silver layer is the exists between these two material, GIS and silver tungstate. Okay, the third photocatalyst is gold zinc oxide, the integrated tungsten oxide nanocomposite. As you can see in this TM image, the gold zinc oxide is perfectly integrated in the tungstate nanosheet. Okay, it is the photocatalytic activity test result. Let's see just two. The photocatalyst. One is the AU loaded zinc oxide tungstate. The image is the this left side, the models. And then second one is the silver zinc oxide, the gold zinc oxide integrated, the nanocomposite. This second, the modeling image. You can understand this. The core cell integrated tungstate composite shows the better performance in this hydrogen production reactions, because it is, I think, the core cell nanoparticle effect. Move. Okay, this is the mechanism. In this quotient nanoparticle integrated the tungstate nano composite systems, this tungstate and zinc oxide perfectly construct the G-scheme, the structure. And then gold is the boost electron to move the upper band edge yes, of zinc oxide band gap at the band edge side. That's why this the composite material shows the very excellent photocatalytic activity, the reactions at especially the band edge side. Okay, next is conclusion and in future work. From these three different research, the result, we can say quotient nanoparticle is the efficiently enhanced photocatalytic activity of the several heterojunction photocatalysts. So in this the future work, we planning to the focus on the more the combination of G-scheme photocatalysts and our the metal red MS quotient nanoparticles. In this study, I will apply this alloy type of the quotient nanoparticle and the nanoload shape of quotient nanoparticles. Okay. Okay, it's my the current the members in my the laboratory. They are working for the two research fields. One is the photocatalyst sensing material by using this quotient nanoparticles. Second researcher, Tran Van Tuong, is alumni of this university, very excellent the researchers. Thank you for your listening and your attention.
Thank you, Professor Yu, for your enlightening presentations. And now, it's my pleasure to introduce our next distinguished speakers, Dr. Huang Lom Zhu. Dr. Zhu brings nearly a decade of expertise in green ammonia synthesis for agriculture and energy applications. Today, Dr. Zhu will share his unique insights on translating research into practical, renewable power ammonia productions, contributing to a more sustainable energy future. Please.
Thank you for your kind introductions, and thank you, VinFuture and the University of Da Nang for inviting me giving this talk today. So today, we'll start. So today, I will share with you how important is ammonia and why it's related to the hydrogen economy and our research at Monash University. So ammonia is the second most important chemical in the world, which is 50% of world population rely on ammonia-based fertilizer. The first human-made ammonia is synthesized by these two Nobel Prize winners, if you know, is Fritz Haber and Carl Bosch. So the Haber-Bosch process, however, is responsible for 2% of the global energy consumption and 400 million tons of the carbon dioxide emissions per annum. But the liquid ammonia contains a high energy density and 5,000 billion US dollar market for the green ammonia. So ammonia using for fertilizer is also used for explosive refrigeration chemicals. Also, ammonia can be applied as a fuel. If you see in the list of fuel here, ammonia is the cheapest one and also the cleanest one. So therefore, in Singapore nowadays, they apply ammonia for bunkering their shipping industry. So energy export, so we can see that Australia has a vast renewable energy resources, and we want to export it. And we can see the same potential for Vietnam. So we choose ammonia over the hydrogen because of non-flammable, for safety. So the liquid ammonia has a higher volumetric energy density compared to the liquid hydrogen. I'm sorry. So and then, so it requires less energy to liquefy and store, lower boil-off rate, which means you can store the ammonia for a longer time compared to liquid hydrogen. And for the infrastructure is well developed because it's inherited from the fertilizer industry. So green ammonia roadmap, so back in 2019, so we released this perspective to emphasize our target to decarbonizing ammonia production using electrochemical process. Therefore, we also drew this milestone for it. So the first generation is the Haber-Bosch process. So the second generation, we decarbonize the Haber-Bosch process by integrated with the water electrolyzer to replace the methane reforming process. And the last generation gonna be the complete electrochemical process. So I'm gonna skip this one. This one is very old one. So at the Monash University, our ammonia research focus on the reduced nitrogen using the redox mediator. So like lithium, so the lithium can react with the nitrogen spontaneously and is from lithium nitride. So this is the only way that we can break the triple bond, the very stable triple bond of nitrogens. And with the alcohol, like in this reaction, we can form the ammonia. So this chemical reaction can be translated into the electrochemical reactions by introduce the electricity, so we can plate the lithium from the lithium source. And we found that calcium and magnesium can do the same job. So when we have the concept, we started building our experimental setup. And we have designed the cell, we have designed the electrolyte, the source. The most important is we developed the robust proton NMR analysis for the ammonia quantifications for the wide range of solvent. So this is the cell that we use for the day one. And now we are scaling up, so we moved the reactor into the flow reactor, but we're still using this one for fundamental study. The first demonstration of the lithium NMR started in 1994. And then until 2019, we retouched and then try to understand the concept. We reproduce the results. After war, we can see that many research groups involved, and then they try to develop the performance. The G-rate has improved, but if you focus on the Faraday efficiency, it's not 100%. And this is very critical to reach 100% Faraday efficiency because it related to the to maximize the energy efficiency. So there's many factors effective 100% improve the Faradic efficiency, which is the proton source and the proton carrier. So to carry the proton from the anode to the cathode, and behavior of the lithium plating, which is closely related to the solid electrolyte interface. So what to do to improve the Faradic efficiency to 100%? So first we have to understand the mechanism of the electrolyte interface. So therefore we have to probing it using the neutron reflectometric technique. So during the HC2 process, we have to quantify the ammonia and make sure we have a decent ammonia and reasonable Faradic efficiency, which is correlated with the observation of the electrode. So this is our example. So we're gonna see, so I don't have a laser pointer here, but you can see when you apply the current, there's a lithium plate on the surface. As soon as the nitrogen and the proton contributes into on the surface, we actually forming ammonia and release the lithium back into the electrolyte, which is show the improvement of the Faradic efficiency. So when we started understanding the mechanism, we started improving the electrolyte interface. So this published in Nature that we investigated different lithium source with a different lithium ion, and we see that the lithium pitch trifluoromethyl sulfonyl amide, which is what you also can call it lithium TFSI or lithium NTF2, very famous in the field of battery, can improve the Faradic efficiency and the U rate significantly. So our understanding is the anion of the lithium NTF2 can create a compact ionic assembly, which is blocking the solvent to attack the lithium and only allow the ethanol and nitrogen to react with lithium and form the ammonia. So therefore, higher concentrations give a higher Faradic efficiency, but we struggle to understand why the Faradic efficiency limit at up to 90%, not 100. And therefore, we start and try to explore more on the surface, and we found this region called triple phase boundary. So the triple phase boundary is the region that have the mix of solid, liquid, and the gas phase. And that actually cause a lot of side products like lithium fluoride, unreacted lithium nitride, and even the lithium polysulfide. So we fix the problem. We resolve the triple phase boundary, and we can extend our performance up to 4 days. And with the break recording past charge of 2.3 10 power for Coulomb per second 2021. And the most importantly, we can achieve Faradic efficiency almost 100%. With the maximum U rate of 530 nanomole per second per cm as well. So let's talk about supplying proton to the lithium ion because it's also very important to balance the reaction. So how the proton carrier work? It actually carry the proton generate from the anode and then move to the cathode where the lithium nitride form, and then protonate to the lithium nitride and form the ammonia. So we try to understand the chemistry of proton carrier, so we come up with the list of the candidates like alcohol group, ammonium, organic acid, and protonated solvent, even water and ionic liquid. So we try to correlate the pKa with the famous parameter in the organic chemistry represent the acidity and basicity. With the performance of ammonia, but we couldn't find the relation here. Therefore, we look into our MIT college, and they proposed the complex stuff, which is solvatochromic parameters. So the alpha stands for acidity and beta stands for the basicity. So we apply into our research, and we could see now is better correlations. So when you increase the acidity from 0 to 0.8, you can see the increase of performance. As soon as you go beyond that, it degrades significantly. And the mystery that still in our hand is like among the alcohol group. In the same research, we found that the ethanol, which is a famous proton shuttle using for many research, is not really stable. So the ethanol can react with the solvent, which is the THF in our research, to form the side product. And the similar reaction happened for isopropanol, but less the degree of effectiveness and give the same performance as the ethanol does. So we have to look for the advanced proton shuttle, which is have the wide range of potential and have zero reaction with the solvent. So then we come up with the phosphonium proton shuttle, which is when the phosphonium donate the proton, it form the E line and they complete the circle to return the phosphonium when it accept another proton. And this chemical cycling efficiency is 100%. Therefore, we add the nitrogen and hydrogen inside, and we could improve it, performance stable for 20 hours, and we can go it longer. And then we can see the linear increasing of the ammoniac U with the Faraday efficiency around 70%. To surpass ethanol, we need to improve the Faraday efficiency up to 90%. And therefore, we look into the mass transport because the phosphonium we use have a long alkyl chain and very bulky. So we try to shorten the alkyl chain and hope that it's gonna improve the mass transport and then improve the performance. However, the results tell us the opposite way. So when we have a higher, the longer alkyl chain actually perform better. And then we look closely to the surface, and it's very interesting that the longer alkyl chain can produce a very smooth and then uniform SCI layer. That means the SCI is very important for the lithium NIR. To balance the mass transport and the SCI, we tune the lithium source concentration, and with the right concentration, we can achieve continuously improve of the ammoniac U and the Faraday efficiency up to 80%. So if you look at the photograph here, you can still see the decomposition of the solvent, which brings us to another problem called acid scenarios. So the first scenario we call oxidize to the polymer and make it locally high proton. Is also let the solvent to oxidize in the same pathway. So therefore, it's applied for all the ether group. And we're looking for the perfect proton carrier and the solvent that inert for the proton. And so let's say, so we understand about the surface, we understand about the lithium source, we understand about the proton shuttle. So now we combine them together and put it to the device. And now we convert the hydrogen source and store it in the form of ammonia. So water will be ideal because water is clean and abundant. And then it can generate the oxygen, which is very helpful for human. And then you can symbolize the whole process and then reduce the cost. However, when you so lithium and water don't like each other. So if you introduce water in the system of lithium and RR, you actually reduce the lithium redox cycling. And when the water and the organic solvent is crossed over, you actually stop the activity in both anode and cathode. So we propose the intercream solutions, which is a hydrogen oxidation reaction. So hydrogen can actually obtain from the water electrolysis, which is the intermediate process. So, so far, this is a cell that we developed at Monash and our spun out Ionic Jupiter company. And we actually couple the lithium NR with the OER, and we could operate it for up to 24 hour and 48 hour with 80% fabric efficiency, and the U rate is reasonable at 25 nanomole per second per cm as well. So when we actually, on the other hand, coupling lithium NR and HOR, we can improve in the rate. So the rate is improved to 80 nanomole per second per cm as well, with the fabric efficiency is 50%. The most important is the solvent didn't decompose. So this showing that this system is very sustainable. So you can convert either water or the hydrogen into ammonia without damage the solvent. Therefore, this can be recycled, the lithium, it can be recycled, proton carrier can be recycled, and the solvent can be recycled. So current and future milestone will be, so we focus on energy efficiency to tackle the challenge of the thermodynamic energy efficiency limited by the lithium and lithium NR, which is 33%. So at Monash University, at the moment, we can improve it to 33% with the strategy improving the electrode and electrolyte. So we submitted this work in Science this year and hope we can share with you the outcome. So the milestone is we, based on the US Department of Energy, and at the Monash University, we has gone halfway with almost 100% fabric efficiency. And with this device, we believe that we can achieve 1 kilogram per day coming soon. So beside that, at Monash University, we also have the different renewable fuel project, like water splitting nitrate synthesis for the fertilizer. And we work closely with our industry partner. And finally, I would like to say thank you to my Monash ammoniac team, the Jupiter Ionics, the lab member, including my students, the funder, Australian government. Again, thank you to VinFuture and the University of Da Nang for inviting me, giving the talk. Thank you for your attention.
Thank you, Dr. Zhu, for that fascinating presentations. And now we turn to our final speakers, Associate Professor Dr. Võ Thắng Nguyên from University of Da Nang, University of Science and Education. Today, she will share her insights on MOF-based material for photo and electrocatalysis. Please join me in welcoming Associate Professor Dr. Võ Thắng Nguyên.
Thank you, Ms. V, for the kindly introduction, and thank you, VinFuture and University of Science and Education, to hold this such a fascinating event for researchers to share the knowledge. So to wrap up the three presentations, I will talk about our research results recently on MOF-based materials for both electro and photocatalytic applications. So why MOF? Why have we chosen MOF material for our research? MOF, the word MOF stands for metal organic framework, and during the past few decades, it has allow an extraordinary achievements in both synthesis of new material and a wide range of different application. As you can see on the slide, it can be used for energy storage and conversion, sensing, catalytic applications, or even environmental management. With this kind of material, you can have different kind of morphology, from like core cell morphologies, from double cell morphologies, or you can even functionalize the surface of the material, so it can have specific functional group on the surface. It means that with a rational design and control of either organic ligands or metal ions, or even the synthesis environment, we can the structure and of course the related property of this material can be adjusted conveniently to meet our specific requirements. So adapting to our practical experimental condition here in UED, we have focused on these three areas. So we try to synthesize morph material for electrochemical analytical techniques, for photo degradation of organic dyes, or for electrochemical water splitting. So I talk about the first is a challenge, environmental problem or quality control of the product is a challenging problem in Vietnam. And to have better quality control, we should have a better method to determine the concentration of different analytes in the samples. And we found that electrochemical techniques will provide us a simple but still reliable way to do that. That's why we try to develop and this is an example of what we did. So in this example, we synthesize the cobalt dop UEO66 materials, and using that as a modifier, the electrode modifier, to simultaneously quantify uric acid and same thing in the sample. And we found that with the use of this modifier, we can clearly detect it. We can clearly detect the both analyzed uric acid and same thing in the sample, especially at the extent of cobalt in the sample. We can obtain the highest peak current, which means that we can detect this analyte at that concentration, but the other electrode can't. There's many factors that affect the performance of the electrodes, but we found that with the use of the modifier, the conductivity of the electrodes has improved a lot. And we propose that the facilitates the electron transfer within the material way to oxidize the analyte. So this is a mechanism of how the analyte is oxidized at the electrode surface, which involve two protons and two electrons. And we use that. We further studied the performance of the electrode for further applications. We found that we can not only simultaneously detect both analytes, but we can also detect single analyte with the presence of the other one. So the presence of either xanthine or uric acid, it does not interfere the determination of the other analytes. And also these electrodes have provided a wide a linear range in a wide concentration range, in either low concentration range or a higher one. When we compare our study with other studies that has been published, we have reasonable results, which mean that it is potential for further application. We also use this electrode to do the quantifications of real urine samples. We have 3 urine samples with a spiking technique, and with the recovery with acceptable recovery. This is our the other related study where we use MOP-based material to modify the electrode and use those electrodes to detect other kind of analytes, from metal ion in the solution to organic analytes in the solution. We do both simultaneously detect two analytes or single analytes. I'll move on to the photocatalytic application of MOF-based materials. As Professor Yu has already mentioned, the use of photocatalysis in different application is very interesting, and through the history, to the development history of this kind of material, we are in the same trend. So we try to synthesize the materials that can harvest much of the solar energy for different purposes. And in our focus, we try to use photocatalysis for the degradation of organic dyes in the water samples. The photocatalyst can be used as itself, but the formation of a composite is more beneficial. I take an example of iron oxide. Iron oxide semiconductor can be used as a photocatalyst. However, because of the fast recombination of the photo-generated electron and holes, its application is limited. However, when we couple that with the other oxides, for example, the other materials, for example, carbon nitride or other oxides, the structure of the electronic structure of the material is changed, and it helps to limit the recombination of the electron and hole, so improving the photocatalytic performance. And in this concept, we synthesize MOF-based material from Brooklyn blue. We anneal that and couple that with titanium dioxide, and using this material to degrade several organic dyes in the solution. And what we found is we actually got the cubic structure, and with the cubic structure with the forming of titanium dioxide on the outers of iron oxide. The photocatalytic properties and other properties, for example, specific surface areas of this material, especially for the 35% of titanium dioxide, is very is suitable for its use as a photocatalyst. And then we use that in the Fenton line hetero system, and that material with 75% of titanium dioxide show greatest performance on the organic dyes such as rhodamine B, methylene orange, and fusion basic. And of course, the mechanism, we believe that there is the arrangement of electronic structure within the material, so suppressing the recombination of photo-generated electron and hole in the materials, and then that will improve the performance of its photocatalytic behavior. We also do the other MOF-based material for this kind of application. For example, we did the MIL 53 for the degradation of methylene orange. Finally, our recent research regarding the electrochemical water splitting to release hydrogen. In this research area, we are now interested in the formation of MOF from nickel. So up to now, there's two material that we interested in. The first one is the formation of nickel MOF on the surface of the nickel foam. And we use 2-methyl-imidazole as the organic ligand, and we tested the hydrogen evolution reaction. And this is result we show that I'll talk about this later. And the second material is also from nickel-based MOF, but then we anneal that to form nickel and nickel oxide composite, and also for electrochemical water splitting. So what we found is the use of different nickel salt will give different performance. In this research, the nickel MOF synthesized from nitrate salts give the best result. Here we do the we examine the table plot to estimate the performance of hydrogen revolution. For the other composite, nickel and nickel oxide composite, we found that the use of different molar ratio of nickel salt and the organic ligand will give a different kind of materials and of course different property of hydrogen evolution. For example, in this on this slide, we can see that different concentration, different amount of organic ligand will form different nickel and nickel oxide with different nickel and nickel oxide molar ratio. And this, of course, affect is performance. In this study, the material with the molar ratio of 1 and 1:2 gives the best results. And the same trend happened when we investigate the influence of annealing temperature and annealing time. So it suggests that there is a suitable ratio of nickel and nickel oxide within the sample to give the best performance of HER. And we propose that metal and nickel oxide and the material to facilitate the forming of hydrogen. So it facilitates the absorption of water on the surface, and it's also facilitate the combination of H plus to form hydrogen gas. In conclusion, so throughout our research work in UED, we have 3 different research areas that serve the idea of sustained development. And of course, there's more to go. And we actually looking forward to use this research result into industry, into practice. And this is what we have. We are trying to do so now. And I also want to acknowledge all of the senior mentors, the research team member, the collaborator, and undergraduate and graduate students to contribute to our research work. And finally, thank you for your attention. Thank you.
Thank you, Associate Professor Dr. Võ Thắng Nguyên, for your insightful presentations. And now we will move on to the most anticipated part of today's event, the Q&A sessions. For our online audience, please feel free to submit your questions in the chat box, and we will direct them to the most relevant panelists. For those who are joining us in this auditorium, please simply raise your hand and we'll bring a microphone to you so that you can speak your question directly. And let's now welcome our distinguished panel of experts back to the stage as we begin the Q&A session. First, I want to say thank you for staying with us. And now we will begin the Q&A sessions. I'm sure that not only me, but also all of our audience are really eager to hear more from your insights. And now I would like to start with the questions from this room. Like, if you have a question, please raise your hand and we will hand you a microphone to ask and talk to our panelists. We have questions from the lady from the first row. Can you please introduce yourself and ask the questions?
Yes. Good morning, everyone. And first of all, I would like to introduce myself. My name is Hương Xuân, and I'm from the Faculty of Physics and Chemistry. And I would like to express my honor to be here to hear about the presentation of three presentation from three researchers. And I would like to say that I'm really interested in your research because I know that the sustainable development is a problem, is a solution to solve the global change, to solve the global problem. And your research open our mind and open the research for our students to apply in the research in the future. And I hope that the materials or the your innovation solution can apply in our students to solve the problem of global and we can apply in the sustainable development. And I have question to you, Seth. I know that the material is very important, and I wonder, are there any plans to test the material in the real sunlight condition or the pilot system outside the lab system? Thank you so much.
And for these questions, I would like now to invite Professor Yu to answer.
Actually, the research work is in the base of the academic stage. I think the power plant system is very important for the application of our materials for some the environmental and energy the industrial side. Yes. In my material, I'm working for the university, so the scale of is limited. But in our lab, we are trying to synthesis of my material of 5 or 10 milliliter, 10 liter reactors. We developed this one, and also we tested photocatalytic activity in the the 10 liter reactors. But more than the bigger size is limited. So yes, maybe we need to the collaborate with company in the future. Okay.
Thank you, Professor Yu, for that insightful questions. And now we also received a few questions from our online audience. And here's one question that is directed to Dr. Zhu. Dr. Zhu, can you please elaborate on the stability and recyclabilities of the lithium metal used in your system, particularly under prolonged operations?
This is the right questions for our development. So as I show in the representations that we actually achieved that milestone. So we showing that we're using the direct oxidize of water and oxidize of hydrogen, which is that we not damage or damage the solvent. So we can reuse the lithium, and especially the lithium is not a pure lithium metal, but it is lithium from the lithium source. So if as soon as it stay in the electrolyte, it can be recycled. And therefore, as I show in the presentation that the whole system at the moment is very sustainable, and then you actually can convert the hydrogen and then store it in the form of ammonia.
Thank you, Dr. Zhu, for that answer. And now I would like to get back to our audience here in this room. I can see a few hands in the back from the students. Oh, I would like to invite the gentleman in the second row first. Can you please introduce yourself first?
Good morning, three researchers and everyone. I am Quỳnh Trần. I'm from Physics and Chemical faculty. I'm Professor Yon Tae-yu. I have a question for you. I'm so excited for your presentation, and thank you for your sharing. And how does the choice of the metaphor, etc., the code affect the photocatalytic efficiency, and are there more cost effective alternative under considerations? Thank you.
Okay, thank you for your very nice questions. Gold is a very important material in my porcelain particles because under the visible light, we introduced some reactions, the photocatalytic reactions. But many people is the asking why gold. Gold is nowadays so expensive. Yes. However, this the visible light absorption is the very good, and then the very stable. And then the electrons is the electron hole pair is the created from this gold core. That's why this gold core is the very the important. And then this gold core is the protected by outer shell. That's why this the durability is also the increase. So I'm using these two things in photocatalyst. In the future, we will change this the core gold part to into the other gold metals or other metal alloys, and ultimately we want to change this gold core to the base metal. It is my the future plan. Yes. Thank you.
Thank you, Professor Yu. And now, after hearing a few questions from our experts and researchers, I would love to hear some more questions from the students in our audience. Is there any students who would like to ask? Oh. Can the technical team please hand the microphone to the student with a red shirt for me?
Good morning, everyone, and we audience very appreciate for your three speaker and your fascinating speaking. You a question, and my question is: in region without ammonia infrastructure, how could your decentralized approach support agriculture and energy needs simultaneously? And that's my question. Thank you.
Yeah, thank you for your questions. Yes, that's the meaning of decentralization. When we decentralize that to serve the remote area, which is cannot achieve the easy to transport or build a habitable plant. So we can, so we talk to our end user, like the farmer. So they actually supporting to have the device, which is using the electrochemical process. And we actually can just locate it with a small site on field, and then we can use local renewable energy, like we have the solar on the rooftop. So we can just use that electricity and run the device, and then convert it into the ammonia we can use for the fertilizer, or we can use that and convert it back into the hydrogen and support for the household. So all in all, the target of using the electrochemical process is to decentralize the ammonia production. And especially very important that we're living in the era of the Internet of Things. So the thing is that we don't need to move, but we still can manage and control the process remotely. Yeah, so that is my answer for you. Thank you.
Thank you, Dr. Zhu. And now I have seen a hand has been raising for several times. So I would like to invite the gentleman in the second row to answer and talk directly to our panelists here.
Okay, thank you very much for your very nice presentation. I want to have a question for Professor Nguyen. I work on medicinal chemistry and organic synthesis, so I really don't have deep knowledge in material chemistry. And everyone know that organic compound has a color due to its long conjugated system. And one application of advanced material is to degrade organic dyes. And I wonder that if the material just only and the organic dye will be a color removed due to the squid of the skirts of the long conjugation system. And I think the most important thing is to confirm what is the product after the photo degradation. It could be more fortunate. It could be less fortunate than the reactant, the organic dyes. But I still don't have any publication, any work to confirm the product of the photo degradation of any organic dyes. Thank you.
Yes, thank you for your questions. Yeah, actually, as you say, in our research, we mostly using UV spectrometry to identify dyes. So we look at the decrease of the absorption peaks, and also we don't have any we didn't see any additional peak after the degradations. Yes, still we couldn't confirm that the final product is carbonic acid and water or other compounds, as you say. But in the future, we will use HPLC to determine the composition in the final degradation solutions to confirm the solutions. Thank you for your suggestion. Thank you.
Thank you, Associate Professor Nguyen. And now I would love to have a student to talk to our speakers next. Can the team please hand the mic to the girl in the back for me, please? Can you please introduce yourself first?
Yeah. Hello, everyone. My name is Islan, and I'm a student at a Bachelor in Physics and Chemistry. And I have a question for Astro and Ferguson Vô Thang Nguyen. Have you observed any trade-off between surface area, conductivity, and stability when converting MOF into the derived form? And what are the most significant challenges in scaling up MOF or MOF-derived catalyst production for industrial water treatment or halogen generation?
Yes, thank you for your questions. Yeah, sure. We have observed some trade-off when we synthesize the MOF-derived material. So there's so many factors that affect the performance of the catalyst, including, for example, surface area, conductivity, the stability. Normally, the MOF materials has higher surface area, but then when we anneal that, the surface area might drop because of the forming of the collapsing of the structure, and also but then the stability of the product is better than the precursor. So we had to balance between different factors that affect the performance of the catalyst. And for the second what's the second part of the question is that they had to scale the material into industrial applications. There are some challenges. For example, mostly the MOF materials is in powder phase, so it's hard to incorporate that into a real industrial treatment system. But then we can think of the way to, for example, more immobilize that in a membrane or in a matrix, to immobilize that and to use that in industrial treatment system. And also, usually to synthesize MOF material, we have to use solvents, which is, I know that it's not good for the environment. So we have to think about the way to switch to the use of, for example, water, so to make it more eco-friendly. So that is our work for the future. Thank you.
Thank you, Associate Professor Nguyen. I'm sure that your answer have provide a lot of insights to our student here. And for one of the last questions, I would love to hear from this side of the auditorium. Is there any students who would like to talk to our distinguished panelists? Okay, it seems like our students have asked a lot of questions. So we are also receiving a lot from the online audience. So for this one, I would like to direct it to Professor Yon Tae-ju from our online audience. Our audience is asking that how does the choice of the metal core, for example, like gold, can affect the photocatalytic efficiency? And are they more cost-effective alternative under considerations for this?
As I said, yeah, in the maybe the first questions, yes, gold is very good material because very stable, and then the visible light absorption is very good. So I select first, and then the synthesis is very easy. Yes, and then we can easily prepare the core shell structure by using this golden particles. But cost problem is existed. So in the future, I will change it. I want to change yes, this material to other materials. For example, the gold-based alloy or gold, the other metal-rich alloy. Yes, and ultimately, yes, the base metal. I will try. Yes, the best to be base metals. Okay, thank you.
Thank you, Professor Yu. And for the last questions that will end our Q&A sessions, I would like to ask Dr. Zhu these questions. In regions without strong existing ammonia infrastructures, how could your decentralized approach support agricultural and energy needs simultaneously?
Can you repeat it one more time, please? Can you repeat it again,
Oh,
please?
yes,
Yeah,
of course.
sorry.
So it's questions from our online audience. Dr. Zhu, in regions without strong existing ammonia infrastructure, how could your decentralized approach support agricultural and energy needs at the same time?
Yeah, so as I say, is the reason we are developing the electrochemical electrolyzer for the ammoniac is to decentralize the ammoniac. So we don't need to transport the ammoniac to the farm or to the household, but we're gonna just replace and store the ammoniac in the device. So you can use the power from the renewable energy to run and to synthesize the ammonia from water, from hydrogens, and therefore we solve the problem of the centralization of the Haber process. So I hope that answers your questions.
Definitely. Thank you. Our engaging Q&A sessions. As we conclude today's event, we would like to extend our deepest thanks to Professor Yon Tae-ju, Dr. Hoàng Long-du, and Associate Professor Võ Thắng Nguyen. And we also want to thank to our wonderful audience for your thoughtful questions and engaging participations, both online and in person. Before we officially close, we are pleased to share an important announcement from our side. Submissions for the 2026 VinFuture Prize is now open. Please, we hope to see you join us in making a positive impact on humanity by nominating innovations that have improved people's life. Once again, thank you all for being here today. We look forward to seeing you again at our future event. And until then, best wishes to everyone.